let's talk about reading from two-component phase diagrams. For this first simple example, I want you to think about a system that is comprised of oil and water. Now, these are components that you are familiar with. You've seen systems, jars that have oil and water. They separate, and we can characterize the amount of oil and water in terms of the fraction. So we can talk either about the mole fraction of oil or the weight fraction of oil that makes this. And for the sake of this first example, I want you to imagine everything being held constant except for the composition. So the temperature, pressure, magnetic field, stress, strain, etc., those are all constant. And if we have a line now, on this line we can characterize the fraction of oil, which I'm going to call X sub O. So let's say this is mole fraction, but it could just as well be weight fraction. Now on the far left-hand side, that corresponds to 0. So it's pure water. And on the far right, that corresponds to a value of 1, meaning pure oil. Now, if you imagine a case which is pure water, you can also imagine putting in a couple molecules of oil. And a couple molecules of oil in a system of water, they go into solution. They don't separate out. So there's a degree of solubility. And we can keep adding oil, and those will continue to go into solution until the solubility limit is reached. And at that point, we're going to have the two separate, and you're going to have a region which is an oil-rich phase and a region which is a water-rich phase. So let's say that we move along here, and that is our solubility limit. And we know that everything is soluble in everything else from the second law of thermodynamics. And now that solubility may be 1 part in a billion, but it's still soluble. If we go over here to the right-hand side, well, pure oil, you put a couple of molecules of water, they go into solution, and as you increase the amount of water, heading leftward, you reach a point where the solubility limit is reached, and you start to precipitate out a water-rich phase and an oil-rich phase. So here, that is the solubility limit of oil, of water in oil. So these two regions, here and here, we have a single phase. This single phase is mostly water with some oil in it. This region is mostly oil with some water in it. But it's still a single phase, as we discussed previously the definition of a phase. When we have a phase diagram, and we're talking about a solid solution, or a solution, this is the two fluids, these aren't solids, but you have a solution, we use lowercase Greek letters to denote the phase. So let's call this alpha, and call this beta. In these phase diagrams, the choice of alpha or beta or gamma or whatever is being used is really arbitrary, and as you go from one phase diagram to the next, those are going to change. So in this region, between the solubility limits, we're going to have a two-phase mixture. And the phases present are alpha plus beta. And the reason we know that is, well, because they're sandwiched between the alpha and the beta phases. Anytime that we have two single-phase regions, there's going to be between them a two-phase region. So now we have a rudimentary phase diagram. And we can start talking about this phase diagram and analyzing what the system will look like. So let's consider that we have a system and we have some composition here. And let's call this XO1, just because it's the first example we're looking at. So if we have a system with composition XO1, we can say to ourselves, well, what phase fraction, or let's say how much of each phase is present. So we call that the phase fraction. So what fraction of this system is alpha? What fraction of the system is beta? So if we were to look at the system, we would see it's all alpha. So let's say F sub alpha is equal to 1, and the phase fraction of beta, F sub beta, is equal to 0. So this tells us how much of each phase is present. The next question we can ask is, what is the composition of the phase, or the phases present? Well, only alpha is present, and we know that the composition is just given by the original composition. So we're going to say X sub O of alpha, so I'm using a superscript alpha to denote the alpha phase, is equal to X sub O1. And this is everything we know about our system from our rudimentary phase diagram. And you can certainly imagine going over here, and we can do exactly the same thing in the single phase beta region of the phase diagram. So now let's pick a different color. I'm going to get blue. And let's say that we picked a composition here. Let's call this XO2. It's our second example. And on our phase diagram, it's sitting in the two-phase region. So alpha and beta phases are both present. So let's first ask ourselves, well, we know two phases are present, alpha and beta. We can read that from the phase diagram. Let's first ask ourselves what the composition of the phases are. So I'm going to write this here. XO alpha, XO beta. So the way to think about this is to think about what we understand from solubility. So think of another system that's simple. Think of the example of sugar and water, or salt and water, right? These are things that you're probably familiar with. You've got some water, you put some sugar in, you stir it, and it goes into solution. You put a little more sugar in, you stir it, it goes into solution. So you still have a single phase region, which is a water phase with some sugar in it. Now you keep putting sugar in, and at some point you reach the solubility limit. And when you reach the solubility limit, you have sugar that precipitates out. So now you've got a liquid that has sugar in it at the solubility limit, and then you've got sugar on the bottom. You put more sugar in, you stir it up, the liquid doesn't change composition at all. It stays at that solubility limit. You just add more sugar to the bottom. So this should kind of trigger in you this thought that if you have a two-phase mixture, the phases have the composition of their solubility limit. So that means that our alpha phase is actually going to have the composition of its solubility limit. So let's call this XO I'm going to call that left, just because it's on the far left side of the two-phase region. So that's going to be the solubility limit of oil in water. And if we want to talk about the solubility limit of water in oil, well, that's going to be over here. And we want to call that XO right. So if you have a system and you're looking at it, you see an oil phase and a water phase, you know that both of those have reached their saturation of water in oil in water, and their compositions are given here and here. So we can write XO alpha is equal to XO left, and XO beta is equal to XO right. So anytime that you're talking about a two-phase region, you can basically look at the left and the right sides of that and read what the composition is of the phases present. So now let's go back and let's talk about what the phase fractions are. So what fraction is alpha and what fraction is beta? So F sub alpha and F sub beta. So let's imagine that this point is actually right here on the far left-hand side. Well, if it is, then, let's say it's right on the border. Well, then it's basically going to be 99% alpha and 1% beta, roughly. In contrast, if we were on the far right side, we would be 99% beta and 1% alpha. And if we were, like right in the very center, we would be about half and half each. What this is telling us is that the way to read the phase fractions is by looking at the ratio of this distance and this distance. So if we want to say that something is mostly alpha with a little bit of beta over here, well, that's going to be close to 1 or close to 100%. So that's going to be this long distance divided by the total distance. And if we said, well, what fraction of this is beta? Well, it's going to be that little sliver divided by the total length. We're basically saying what fraction of this line is close to alpha, what fraction is close to beta. And we call this the inverse lever rule in kind of the common language of reading phase diagrams. And the reason people call it that is because you are in the two-phase region, and in order to talk about the fraction of alpha, you look at the distance here to here, which is away from the alpha, because it's not nearest the alpha phase, and divide that by the total length. So the fraction of alpha, in our case, is going to be given by x0 right minus x02 divided by x0 right minus x0 left. So x0 right minus x0 2 is that distance, and x0 right minus x0 left is that distance. And you can certainly imagine to yourself that as this moves, if we were to change composition further and further this way, as x02 approaches x0 left, well, that's going to be right minus left over right minus left is going to be 1. And if this x02 were to start moving and we were to make a composition closer and closer to x0 right, well then it would be x0 right minus x0 right divided by the denominator. It's going to be 0. So this equation fits with our intuition and from our understanding of looking at this diagram. Now, if we want to talk about the fraction of beta, what you could do is, I'm going to grab a purple marker here. What you could do is you could say, well, it's going to be this distance divided by this distance. So that's going to be x02 minus x0 left divided by x0 right minus x0 left. You could do that, or you could recognize the fact that the fraction of alpha plus the fraction of beta is equal to 1, right? That has to be 1 because our system we're looking at, it's either alpha or beta or it doesn't exist. So these have to be equal, which means we could also write f beta is equal to 1 minus f alpha. And that is something that on a quiz or a homework assignment is going to be a lot easier and a lot faster. So this is the basics of reading a binary phase diagram. And then in this binary phase diagram, we kept temperature, pressure, etc. constant. Now I want to point out that we can change those and we can make a diagram that's not just a straight line. So for example, let me erase this. So this was our original temperature. Let's say now this is, we're going to hold pressure and everything constant, but we're going to allow temperature to vary. And this can be our original temperature. We have our solubility limits. This is a solubility of oil and water. That's the solubility of water in oil. And our intuition tells us that as we increase the temperature, typically solubility increases. Right? That's what happens when you're putting sugar in water, salt in water. And at the same time as we decrease the temperature, the solubility decreases. So that means that as we go down in temperature, this is going to go this way. And as we go up in temperature, it's going to go like this. And the beta is going to look like this. So now we have a way to think about this phase diagram as a function of composition. In this case, the mole fraction oil and the temperature. And what this also tells us is that at any temperature, let's just draw this out a little bit more. We're not going to think about the details of this, but at any given temperature, what we're basically going to do, let's say, we know this point, but let's say we have another temperature, say right here, call this T star, that's our temperature of interest, and let's say we have a composition here, XO star, again, to say that it's our composition of interest. Well, what we can do is we can go up, go over. We can see that we're in the two-phase region, so our system is a mixture of two phases. And now what we can do is we can draw a line here to here. We can draw a vertical line where we're touching the phase boundaries in the diagram, and these phase boundaries, again, this is our solubility limit, just like we talked about before. So that point is XO alpha. That is the oil composition of the alpha, and this point, we drop a vertical line down. That point is XO beta. It's the amount of oil in the beta phase in our two-phase region. And now we can talk about the phase fraction. So we say, okay, at this point and at this temperature, what fraction of alpha, what fraction of beta do we have? So, well, we know that the fraction of alpha is going to be given by this distance divided by this distance. So, fraction of alpha is equal to x0 beta minus x0 star divided by x0 beta minus x0 alpha. And the fraction of beta, f beta, is equal to 1 minus f alpha, because we're lazy. We could write it out if we wanted to, but we don't really need to because we know they have to sum to 1. And this is the basics of reading binary phase diagrams.